Welcome to the channel. Hope each and one of you is having a wonderful day. Today we'll be looking at this problem called combination sum. And so in this problem we're given a set of candidate numbers called candidates without duplicates and a target number, target, and we want to find all unique combinations in candidates where the candidate numbers sum to target. The same repeated number may be chosen from candidates unlimited number of times. And a couple of notes. All numbers, including target, will be positive integers. Solution set must not contain duplicate combinations. So if you see here, we have the candidates 2, 3, 6, 7, and the target is 7. And so one of our solution set has 7. Well, that's because sum of array of just 7 is 7, so it meets the target. And then another array, we have 2, 2, 3. The sum of that, 2, 4, 7, also sums up to 7. And of all the combinations with 2, 3, 6, or 7, where we could choose unlimited numbers, that is all the possibilities. So this is the result that we return. So we check this, candidates 2, 3, 5, and the target's 8. So we have all 2's, that sums up to 8, and 2, 3, 3, and 3, 5 as well. So now we understand a little bit how the problem works, and so now I'll explain the main idea for this problem, for the approach. So if we take our example where we have 2, 3, 6, 7, and we have target equals 7, what we can do is we can sort the list in increasing order, and then we add 2 until we reach the target or we exceed the target. So we go 2, 2, 2, 2. Now we see that it exceeds the target. So what we do now is we can do backtracking. So we remove the 2, and then we go through 2, 2, 2, 2. And then we move on to the next number since we're done with 2's, and we try 3. And that also exceeds, so we continue, and then we do try 6, and we also try 7, but thing is we should stop at 3 since we know that all the numbers are sorted in increasing order. There's no possibility, so we backtrack once more. Once we have 2, 2, we just backtracked, so now we try 3, and that equals 7. So now we append this to our results. And so we have our backtracked solution with 2, 2, 2, and we try 6, and that yields a number that exceeds our target of 7. So we would end, and we would backtrack and not check the rest of what is in the array. And so once we are done with processing the 2's, we continue this pattern for each of the elements in our candidates. And so when we have 7, later we'll start with 7, and we will find that it's equal to the target, so we append that to the result. So let's try to code this up and proceed. So one thing is we need to have our results array, store all the results, and we'll return that later. We also said that we wanted to sort our candidates, so we do that here. And then essentially we're doing depth first search because after we have the elements sorted in increasing order, we start with the smallest element and we add that as many times as possible. So let's call this function DFS, and we need to feed in the target so we know that we reach the target or exceed the target. And then the current result will be empty, and we'll add to that. And we have this 0 indicating what indice we are on. That way when we backtrack, we know which number to try next. So an example is we had 2, 3, 6, 7. If we backtrack from 2, then we want to make sure our indice would be offset. That way next time we know we try 3 and not try a 2 again. So once you perform all that depth first search, then we'll return the results. Now we could write the depth first search, feed in the target. We'll call this the path, and then IDX for index. First thing we check is if the target were 0, then it means that we have a combination that sums up to the target. So if the target is 0, if we do not target, then we have our current path is a combination. So we'll append the current path to our results. Other case is that we don't have a sum that is a 0. Our target is not equal to our sum of our path. The sum of our path is not equal to 0. In this case, we have to iterate through all the rest of the numbers, including the index and after. And so we use enumerate for that. We choose from our candidates that we have sorted, and we don't choose any elements before the index because we're applying backtracking. Now, a case is possible that our value is greater than our target. So an example would be the target has 2 currently, and the value we're on is 3, and it means that 3 cannot be used in this combination. So we would break from the for loop, and we would not evaluate the rest because we know that those numbers would be greater than 3. So they will also not work. However, the other case is that we do have a value that is less than the target or equal to the target. So we will perform DFS, and we'll do the target subtracting from the value, meaning we're including it in our combination. And to include something in our combination, we add it to our path. And we also use the index to make sure, and we add it by I, so we know that we're offsetting, so that next time we are including the current, we're never checking an element that is before the current index. So yeah, let's try to run this and see if it's good. Okay, so A is not defined. Right, so that's candidates. All right, so it looks like running this works, and let's try another example where things are not so, well, we have 2, 3, 5. Let's try that one. Okay, looks good. Just in case, let's see if we have something that's not sorted, if it would still work. Okay, also looks good. So let's try submitting this. Awesome, so it's accepted, and yeah. All right, well, we could talk about the runtime for this solution. So we have let's pull this. Is it possible to pull this down? Well, in any case, we call DFS equal to the number of candidates, or the smallest candidate, target value divided by smallest candidate. And each time we do that, okay, seems like it's a little hard to explain. Yeah, so we are calling DFS. Number of times we call DFS is our target divided by the smallest element's value. And then each time that happens, okay, so the worst case for this runtime is that each of the candidates, the worst case runtime is number of times we call DFS. And then the number of times we call DFS, we have to iterate candidates. So worst case is we iterate all candidates, so number of candidates equals n. And DFS, most time we would call DFS is target value divided by smallest number in candidates. And we'll call that M. And the other thing is we're also sorting. So we sort first, which is, let's say, yeah, we said the number of candidates n, so that's n log n. So it looks like the runtime would be our sorting, so that's n log n. And then we add our DFS and backtracking, which is m times n. So this m times n, each time after we perform DFS once, we will go through the for loop and then perform other DFS. So I do think that it's a little bit greater than m times n, and m times n would be, right, it could be smaller than n log n. So there's different cases where n log n is bigger than m times n, or n log n is smaller than m times n. And so if m times n was bigger, and I think this m times n is a lower bound, and I think it's a little hard for me to calculate the exact runtime, but for this part, sorting, and then we have backtracking. We know our backtracking is better than the official worst case, which is all combinations, which is factorial. Yeah, so basically our runtime would be bound by n log n plus m times n. And our space complexity is dependent on the longest path that we can make, which would be, yeah, the longest path that we can make. So Yeah, that would also be bound by m, the target values divided by smallest number. But that's just the worst case for one of the space. Oh, actually, yeah, because I'm reusing that space. But also recursion takes up space for the recursive calls. Well, in any case, I'm having a little bit of trouble calculating a very tight bound for runtime and space complexity. But the range at which the algorithm for time is bound between factorial and backtracking. Yeah, for the backtracking between m times n and factorial, that's where the runtime lies, is definitely more optimal than the ultimate worst case, which is factorial. So that does show that the solution is a slight optimization. But yeah, if any of you guys want to let me know what your calculation is for the runtime with a tighter bound and space complexity, yeah, please let me know in the comments below. And yeah, I'll be very excited to learn and learn from you as well. But anyways, that's the video for today. Hope you guys learned a new way to solve this problem, and well, learned anything. If you learn anything, that make me happy, because that's the purpose of these videos. But also, yeah, please leave any suggestions or ideas in the comments, especially, yeah, anything about runtime and space complexity in the comments below. That would be great, and I hope all of you have a great rest of the day. And yeah, see you guys in the next one.